Hi, in this video we're going to go through some worked examples on finding the basis and dimension of various vector spaces. Let's begin with a problem using the row space algorithm. We want to find a basis for the linear span of a given set of vectors, shown here, and we want to do this in such a way that the basis vectors have as many zeros in them as possible. As we do this, we want to keep track of the dimension of the space and what the parent space is. I recommend you pause your video at this point, try to work through the solution on your own, and then resume to watch the worked solution. This kind of problem, where we're trying to find a basis that has as many zeros as we can possibly find, is best approached using the so-called row space algorithm, where we create a matrix whose rows are the given vectors, and then carry out Gaussian elimination all the way to the reduced row echelon form, where the rows will have many zeros. Important to keep in mind that no matter how we've written the original set, we've written them as column vectors here, we have to construct a matrix where the rows are the original vectors. So the first row is 1, 2, 2, 1. The second row is 2, 2, 1, 1. The third row, 3, 0, 3, 1. And the fourth, 1, negative 2, 2, negative 1, to match the given vectors. Then we simply carry out Gaussian elimination using the process that by now should be quite familiar. We start in the upper left and eliminate downwards. 2 minus the first row the second row minus 2 times the first row. 2 minus 2 is 0. 2 minus 4 is negative 2. 1 minus 4 is negative 3. 1 minus 2 is negative 1. The third row minus 3 times the first row. 1 minus 3 is 0. 0 minus 6 is negative 6. 1 minus 6 is negative 5. 0 minus 3 is negative 3. And the fourth row minus the first row. 1 minus 1 is 0. Negative 2 minus 2 is negative 4. 2 minus 2 is 0. And negative 1 minus 1 is negative 2. We've zeroed out underneath the first pivot, so we move over and down to our next pivot and eliminate downward again. The third row minus 3 times the second row. 6 minus negative 6, or 6 plus 6 is 0. Negative 5 plus 9 is 4. Negative 3 plus 3 is 0. And the fourth row minus 2 times the second row. Negative 4 plus 2 is 0. 0 plus 6 is 6. And negative 2 plus 2 is 0. We've eliminated all of the entries below our next pivot, so we move over and down and repeat. Here, our fourth row is simply a scalar multiple of our third row, so it's going to become all zeros in this step. At this point, we have echelon form, upper triangular form, but we don't stop. We have enough information to find a basis here, but if we want a basis that has as many zeros as possible, we need to continue the back substitution process to reduce the row echelon form. We scale our bottom pivot by dividing through by 4, and then use that to eliminate upwards. This is easy in this case because we have zeros everywhere except for this third position, which means when we subtract multiples of this row, we just eliminate the entries in this column without affecting the others. We then move up to our next row. We want to scale this, dividing through by negative 2 to give 0, 1, negative 2. and eliminate upwards, noting that we add this second row to the first, and this will zero out this position and this position. This leads us to our reduced row echelon form, where each pivot is one by itself in a column of otherwise zeros. And we are ready to pull out our zero-rich basis. The non-zero rows of this reduced row echelon form are a basis. Because we've gone all the way to the reduced row echelon form, each of these has many zeros. Always good idea, good form to use the same representation for our basis as we started with. We started with vectors that were in columns. We'll write our basis in the same form. Although we're going to write these as columns, they come from the rows. The first row gives us 1, 0, 0, 0. The second row gives us 0, 1, 0, half. And the third row gives us 0, 0, 1, 0. The number of non-zero entries, or not non-zero rows, the number of vectors in our basis is the dimension of the vector space. It's 3 in this case. And we identify the parent space by simply looking at how many elements did our vectors have. 4 vectors, that means they were from R4. This set of vectors spans a 3-dimensional subspace of R4. Always a good idea to keep track of the parent space and the dimension, partly for intuitive understanding, to see really what does our space look like in an abstract sense, as well as to catch errors. If, for example, we ended up with a dimension of more than the dimension of the parent space, this could be an indication that something has gone wrong. Now let's consider a second example. Again, finding a basis for a given, for the linear span of a given set of vectors. But in this case, where we're looking for a basis that is a subset of the original set. That is, we want our basis vectors to include only vectors from these 4 that are given. And again, we will use our keep track of the dimension of the space and the parent space as we go ahead. I recommend once again you pause your video, work through the problem on your own, and then move forward to check your work against mine. This kind of problem, where what we want is a basis that is drawn from the original set, is best solved with the casting out algorithm. This begins by creating a matrix whose columns are the vectors. It does not matter how we present the original vectors, they need to become the columns. In this case, they were presented as columns, and so the matrix we work with is really simply combining these vectors into a single vector: 1, 2, 1, 2, 4, 2, 1, 3, 2, and 1, 1, 0. And then we're ready to begin. Once again, we carry out Gaussian elimination, starting in the upper left, eliminating downwards. The second row, minus 2 times the first. 2 minus 2 is 0. 4 minus 4 is 0. 3 minus 2 is 1. And 1 minus 2 is negative 1. The third row minus the first. 1 minus 1 is 0. 2 minus 2 is 0. 2 minus 1 is 1. And 0 minus 1 is negative 1. We've zeroed out underneath the first pivot, so we move over and down. We have a 0 with only zeros below. So we shift over to our next column and use this as our pivot to eliminate downwards. The third row is a scalar multiple, in fact identical to the second row, and so when we do that, we're going to end up with a row of all zeros. We have two pivots. We are in our echelon form. When we're simply trying to find a basis using the casting out algorithm, there is no benefit to continuing on to the reduced row echelon form, so we can simply stop here. The reason there's no benefit to continuing on is that to find our basis, we need to go back to the original matrix. Very important part of this approach. We identify the pivot columns from our echelon form. The pivot columns are 1 and 3. And so we highlight those same columns from the original matrix, and those become our basis vectors. 1, 2, 1, column 1, and 1, 3, 2, column 3. Once again, we use the same form representing our basis as we were given. The number of pivots, 1, 2, the number of basis vectors, 1, 2, is the dimension of this vector space. The parent space is defined by how many elements each vector had, 1, 2, 3. R3, or three-dimensional space, is the parent space for this span. These four vectors in three-dimensional space span only a two-dimensional vector space, a plane in 3 dimensions. Okay. Now let's move on to our last example, but one that involves multiple pieces. Can we find the dimension and a basis for all 4 of the fundamental subspaces of the matrix given here? Once again, I recommend you pause, try to solve this problem on your own, and then move forward to compare your solution to my worked example. We begin this process anytime we're interested in understanding the structure of the matrix subspaces, their basis, their bases, their dimension, and so on. Always begin with Gaussian elimination, at least to echelon form, and there's benefits to going all the way to reduced row echelon form. So let's walk through this. We start with our matrix. In this case, we're given a matrix. We don't have to construct it. Eliminate downwards with our first pivot. The second row minus 2 times the first. 2 minus 2 is 0. Negative 2 plus 2 is 0. 2 minus 4 is negative 4. Negative 2 minus 2 is negative 4. And 2 minus 6 is negative 4. The third row plus the first. Negative 1 plus 1 is 0. 1 plus negative 1 is 0. 1 plus 2 is 3. 2 plus 1 is 3. And 0 plus 3 is 3. We've zeroed out underneath our first pivot. We move over and down. We have a 0 with only zeros below, so we move over to our next pivot and eliminate downward again. Once again, here we have a third row that is a scalar multiple of the second row, and so it's going to become all zeros in elimination. We have here our upper echelon form. We could pull out a basis for the column space simply with this. We could pull out a basis for the row space simply with this. It will be easier to pull out a basis for the null space if we take the extra step of going over to the reduced row echelon form. And so let's do that. It will also give us a simpler form for the row space by doing this. So to move to reduced row echelon, we scale the second row, dividing through by -4, giving us 0, 0, 1, 1, 1. And then use this to eliminate upwards, basically adding -2 to each of the three last columns, giving us 1, -1, 0, -1, 1. We have pivots in columns that are all zeros except for the 1 in the pivot position, our reduced row echelon form here. Okay, now that we have our reduced row echelon form, let's pull out as much information from it as we can. First of all, the rows of any echelon form are a basis for the row space. So we can take our reduced row echelon form and simply draw out the rows. I should emphasize these are the non-zero rows. Our first basis vector, 1, -1, 0, -1, 1, which I've written here in column form, and our second basis vector, 0, 0, 1, 1, 1, which I've written in column form here. There are two non-zero rows, two basis vectors in the row space. The dimension of the row space is 3. The row space vectors, each one has 5 elements, and so the row space is a subspace of 5-dimensional space, of R5. Okay. Also from the reduced row echelon form and the original matrix, we can pull out a basis for the column space. The pivot columns of the original matrix are a basis for the column space. We had pivots in positions, columns 1 and 3. So we pull out column 1 and column 3, and these are a basis for the column space. 1, 2, -1, the first column, 2, 0, 1, the third column. The number of pivots is the dimension of the column space. Dimension of the column space is 2. 2 basis vectors in a basis. The column space, each vector has 3 elements, so belongs to R3. The column space of this matrix is a 2-dimensional subspace, a plane in 3-dimensional space. There's a check here that is implicit or is built into the process. We should always double check that it is in fact true. The row space that we just found had dimension 2. The column space also needs to have dimension 2. Row space and column space always have the same dimension. Now that we've found the row space and the column space, basis and dimension, we can move on to the null space. The null space has a basis given by the special solutions, either to AX equals 0 or equivalently to Rx equals 0, the reduced row echelon form. This is where having gone all the way to the reduced row echelon makes things easier, because as we've seen before, we can pull out the special solutions directly from this matrix with no extra work. We identify the number of free variables. Free variables are at x2, x4, and x5. There's 3 of them, so the dimension of the null space is 3. We find those by, in turn, setting each free variable to 1 with the others equal to 0. So we start off with x2 being 1 and x4 and 5 being 0. That means we are working in the second column where our non-zero free variable is, and we read off the pivots for x1 as negative of -1 or 1, and for x3, 0, to give us our first entry, our first vector. 1, 1, 0, 0, 0, that is our first basis vector. For our second, we set x4 equals to 1, and x5 and x2 equal to 0. Then we go over to the fourth column, because this is the one where we had a non-zero free variable, and pull out the entries again. For x1, we have a -1, or 1, and for x3, we have -1. For so our second basis vector, 1, 0, -1, 1, 0, is placed here. Our last one comes from setting x5 equal to 0 and x5 equal to 1 and x2 and x4 equal to 0. We're drawing now from our last column both the x1 and the x3 entry here are 1s, which we negate in our final answer. -1, -1. -1, 0, -1, 0, 1 is our third basis vector for the null space. The null space has dimension 3. Each of the null space vectors has 5 elements. It lives in its parent space is R5, 5-dimensional space. Okay, we've now found basis and dimension for the row space, the column space, and the null space, all of which we were able to get directly from the reduced row echelon form of our starting matrix. The last one, the left null space, is less straightforward. So there's an extra slide in there. Is a little bit less straightforward to get. We need to do some more work. The left null space are the special solutions to A transpose y equals 0. The simplest way to find this is actually to carry through Gaussian elimination on the transpose of this. So we simply take all of the columns of A and make them the rows, and then carry through Gaussian elimination. As always, eliminating downward. Second row plus the first gives us 0, 0, and 0. The third row minus 2 times the first gives us 2 minus 0 is, 2 minus 2 is 0. 0 minus 2 is -4. 1 minus -2 is 3. The fourth row minus the first row, 1 minus 1 is 0. -2 minus 4, minus 2 is -4. 2 minus -1 is 3. And the last fifth row minus 3 times the first row. 3 minus 3 is 0. 2 minus 6 is negative 4. 0 minus negative 3 is plus 3. Sorry for the slight overlap here. There's a spacing issue on this slide that I'll fix on the ones I post. We've zeroed out underneath the first pivot. We move over. We see we have a 0, but non-zero is below. We can achieve a row swap. And I'm going to combine two steps here because I notice that actually all of these rows are exactly the same, which means the next elimination step is going to zero out these bottom ones, leaving us with an echelon form of, as shown here. Easiest to pull out the solutions if we go all the way to our, sorry, this is not the right final answer here, so I apologize for that. Go all the way to reduced row echelon form. We scale this second row, dividing through by 4, giving us 1, 0, 1, and negative 3 over 4. And then we use this to eliminate upwards, subtracting 2 times the second row from the first. 1 minus 0 is 1, 2 minus 2 is 0, and negative 1 minus negative 3 halves is plus 1 half. This gives us our reduced row echelon form. So let's just call this R. And from this, we can pull out our final answer. We identify the free variables, that is x3. There is only one of them, which means the left null space has a dimension of 1. We find a basis for that by setting the free variable equal to 1. Our free variable equals 1, and getting the additional entries in that from the column corresponding to this. The first pivot gives us negative half, and the second pivot gives us negative 3/4, or 3/4. Our single vector for the basis of the left null space is negative half, 3/4, 1. We see this null space, left null space vector has 3 elements. It lives in R3. Its parent space is R3. The left null space is a one-dimensional subspace of R3, a line in 3-dimensional space. We've now found a basis for and the dimension of each of the 4 fundamental subspaces. It's always a good idea to just do a couple of sanity checks to make sure that we didn't make silly mistakes. Double check the dimensions and make sure they all match up properly and that the sizes of the vectors all make sense. Remember that the row space and the null space live in the same parent space and have dimension that has to add up to the dimension of that. They both were subspaces of R5. The dimension of the row space plus the dimension of the null space, 2 plus 3 equals 5. The dimensions work out. The column space and the left null space both were subspaces of R3. 2 plus 1 equals 3. These dimensions match. If there's a mismatch, if the sum of the null space and the row space don't equal their parent space, if the dimension of the column space and left null space don't match their parent space, we know that there's a mistake. Everything that was done here was able to be found with one sweep through of Gaussian elimination through the matrix, with the sole exception of the left null space. Actually, even without that last step of working through with a transpose, we can get partial information about the left null space. We can always find the dimension of the left null space simply by taking the difference of the parent space. And so in some cases, we can avoid that second piece of, that extra piece of work. But if we do need a basis for the left null space, we need to go through that last extra step. So with that, we've gone through a number of examples. An example of using the row space algorithm to find a basis for a spanning set. We've seen an example using the casting out algorithm to find a basis given a spanning set. These two different approaches give bases that have different properties. The row space algorithm gives a basis with lots of zeros. The casting out algorithm gives a basis that is composed of elements from the starting set. And we've gone through the problem of looking at finding all of the fundamental subspaces, the row space, column space, null space, and left null space for a given matrix. That wraps up the videos for Unit 7. Thank you, and goodbye.